So, as announced, I want to explain a few code constructions, mostly the CSS construction and its relation with homology. And but there are many constructors. There's even a because there's so many constructions, there's even a zoo where you can see sort of all the animals. And where's Victor? There's a zookeeper. I can't even see when he raises his hand because there's too many people. Okay, Victor is here. Victor Albert. He set up this error correction zoo. And so if you want to contribute, you have a new code, you will say, hey, maybe somebody already knows it, or I want to add it to the zoo, go to this this website. And so I think that's a very nice platform to share codes and things like that. All right. So I want to talk about CSS codes and homology because it's a way to construct codes from manifolds, from tiling manifolds. So it's a rich platform to develop codes, and it's also a central component or somewhat central component in the newer good quantum LDPC codes, because you can kind of take tensor products of chain complexes, and then there's further things that you need to do. And so this is sort of the basics, to understand, if you want to understand some of that. And CSS code, Kellerbranch, Shore, and Steen were also one of the first codes. There's a particular class of stabilizer codes, and the defining feature is that this parity, the stabilizer has these generators, and for CSS code, they are generators which only use poly X. They're the X-type generators, and they're generators that only use poly Z, and they're the Z-type generators. And for the CSS code, you get these X-type checks and the Z-type checks from two classical codes. And so that's a way of that's the original construction. Now, of course, there are stabilizer codes that do not fall in this formalism, they have mixed types. There's some XXZ code or XZ code that people would be interested. There's also codes that use the Y checks, and it's also interesting to study those and see whether they have, added benefits in some sense than these CSS type codes or homological codes. Okay, so let's review this. So what we start with is some things from homology. And so we start with something that's called a chain complex. And this is over Z2. That's to say, what we have is vector spaces, C0, C1, and C2. And you can just see these as, and there are some dimensions. So of C2 is Rx, and of C1 is N. This is suggestive of qubits. So basically, we have an n-dimensional vectors with entries which are 0 and 1, and also because this is Z2, sorry. Right? And now you can just see these as vectors, and then you can have matrices, of course, mapping one binary vector onto another binary vector, and I can call these maps. So and the map from C2 to C1 is called delta 2, and the map from C1 to C0 is delta 1. And there is one essential property that makes this a chain complex, is that these maps have, if you compose them, they get 0. So that's to say you start with any element in C2, and so that's a vector of length Rx with some 1s and 0s. Then you apply this particular boundary map. It has some specific action, and the boundary, it says boundary map, and that is actually really, geometrically what this will mean. And then you have an element in C1, and then you apply the boundary map again, and then you get nothing. So you don't get a vector back here. So you're sort of in the kernel of this composed map, or the input is in the kernel. And this also is said that the boundary of the boundary is 0. And so geometrically, what we should think about is that we have, for this kind of things with these labels 0, 1, 2, we have, we're tiling a surface And this is, say, a closed surface, could be a ball or a torus or something. And we're tiling this with some faces. They could be triangles or squares or pentagons, whatever I choose. And then every face is an element in C2. So every face is, so there are sort of Rx of these faces. And with the particular face, I associate the vector with all zeros and a 1 at a particular location. Right? So, and then, of course, if I have a collection of faces, I just add these vectors. So I have some other vector in C2. And now the idea of this boundary map is that it takes the boundary of these faces. And the boundary of the face are the edges that are around it. And you see that, faces are two-dimensional. That's why there's a 2 here. And the edges are one-dimensional. That's why there's a 1 here. So if I take a thing with a single face, then the boundary map, del2, will map it onto 4 edges. So this will be vector with 4 1s somewhere at the location of these edges. And so my surface, I will have n of these edges. And if I think about a surface code, this is where I'll put my qubits on these n edges. All right, but now, okay, so now if I started with this face, now I have the boundary, these 4 edges. Now again, I can take the boundary of a collection of edges, right? And then it's clear that if I take the boundary of this guy, I will get 0 because, every vertex occurs twice, and I do addition modulo 2, so I get the 0 vector, right? And so that is the meaning of this, that the boundary of a boundary, if I start with any collection of faces, I take the boundary edges, and then I'm not left with any vertices. So in general, if I just take any edge here, of course, the boundary will be the vertices at the endpoint. Okay, so that is the chain complex. And now the CSS construction is where you can say these maps, like they're just matrices mapping from, binary matrices mapping from one binary vector space to another. And these you can just read as parity check matrices of a classical code. You could either, you could say, okay, I got the parity check matrix of 2 classical codes, but I need to have some condition, and that makes a chain complex. Or I say I have some surface or some manifold, and that generates 2 classical codes which have a certain relation. Okay, so we have, so the relation is this. Del2, so for example, here we have the example of the Hamming code for which you can do this. So this takes, so Rx is 3 and n is 7, and we have a parity check matrix. So if I apply this to code words, classically the parity check is when you do these parity checks on these 7 qubits. So you look at the parity of 1, the first bit, the third bit, and the 5th bit, and the 7th bit, and that should be, even. That's what the parity check says for the classical code. And that puts a condition on the code words that you apply it to. Okay, and then the del2 transpose, because it acts sort of the other way, it is h of x, the parity check of another classical code on n bits. And then, this condition, if you just apply this, it just means this property. And it means that if you look at the rows and the columns of this, they have to be orthogonal. And that condition is exactly, we said if you have a stabilizer group, you have your parity checks, and now you only have z checks and x checks, and they have to commute, right? And so the point is that the parity checks, in order to commute, they have to have an even overlap then. And if you have 2 binary vectors and they have to be orthogonal, they have to have an even overlap in order to be orthogonal. So that's expressed by this, right? Okay, so that's the, okay, so now this thing above you can kind of almost neglect, because the thing is what you do is with these parity check matrices, you take, if you've seen this CSS construction before, you take your parity check matrices, and instead of having these 1s for one of the matrices, say HZ, you replace it by Z Paulis, and the other one you replace by X Paulis. So everywhere there's a 1, you replace it by a Z, and everywhere in the other matrix there's a 1, you replace it by X. Yeah, and this is a concise way of writing this. And it's, yeah, okay, so let's, actually, this should be a Z2 here, sorry. Yeah, and this is the way, so for the Steen code, we can take this, you could actually take this code, and you take this code for both HZ and HX, and then you encode, so you have 7 qubits, and you encode 1 qubit. Okay, so what do, oh yeah, so now the other property, so, sorry. Yeah, okay, so we can relate it to the stabilizer group. But now the essential property why you want to use a chain complex to construct a code. Okay, so first the chain complex gives you that you get an abelian stabilizer group, so that's nice, right? But now of course we care about codes with a very good distance. And so the distance, you can ask, also relates to the homology of this chain complex. Okay, so let's look at this, this group. This is the first homology group. First, because there's a 1 here, and because we're talking about the kernel of del 1. Right, so what is the kernel of del 1? Del 1 acts on edges, and so if in order to be in the kernel, I should have a collection of edges that has no boundaries, right? So I should just have a closed loop, right? That is a closed loop. And but actually, what this kernel is, I should not include the image of del 2. What's the image of del 2? Well, I take a face, right? That's an element in the C2, and I just look at it, what it's mapped onto, and they'll be mapped onto some closed loops, right? And it's clear, for example, if I were to do this for the sphere, then I can maybe understand that there will be nothing in here. That's to say, everything that is in the kerr of del 1 is also in the image of del 2, because there are no loops that are not the boundary of some surface, right? Whereas if I do this for the torus, I can have loops around the torus which are not the boundary of a surface, right? And so those loops that are not the boundary of a surface are in this homology group. Yeah, so they're, yeah, so that's what this says. And the dimension of this homology group is then maybe K, and because there's sort of K of these loops. For example, for the torus, I have this one and I have that one. And so there are two, ones that are independent. And so I encode 2 qubits essentially. So this relates to the logical operators. So I have, in general, if this homology group is k-dimensional, I have k-encoded qubits with these logical operators. Now, if I do this for surfaces, you can go to the, and you have tiles, you can go to the dual lattice, right? You can generate some lattice, let's say of these squares, and you can go to the dual lattice in which every face becomes a vertex and edges stay edges, and every vertex becomes a face. And then you have what's called a cochain complex, and the homology group there gives you the logical X operators. But that's not so important, at least that if you just look at this group, it will give you the dimension of the code space and the logical Z operators, and it's a matter of finding, and how many there are, a matter of finding the matching logical X operators. And now the point, of course, is about the distance, is that if I tile this surface, if I have many, if I tile my torus with many tiles, this loop operator that goes around the handle will be touching many edges, and there's really no way to make this have a shortcut, and that lower bounds the distance of the code, right? So this is the old, I guess Kitaev was the person who introduced the Torah code and had this insight, and then was also generalized with insight with Mike Friedman and many other people later. Okay, so this is, I sort of already mentioned that here you see the two logical loops on the over the torus. If I have periodic boundary conditions, and the matching logical X is sort of a loop on the dual lattice, and this logical X1 anti-commutes with this logical Z1, and the same here, right? Okay, so now I want to, sort of, the point of this construction is you can start with a three-dimensional chain complex where you have C0, C1, C2, and C3, right? C3 would be cubes. And then you can say, okay, where I'm going to put so for a code, I need sort of 3 levels, right? Because if I, like, for example, I did this for my surface, I have one type of check is associated with basically the vertices, the other one with the faces, and I put the qubits on the edges on the one-dimensional object. So if I have a hyperdimensional object, I can say, oh, I have C1, C2, C3, C4, so I can put my qubits on either C1 or C2, and often that actually doesn't make a difference. So if I put them on C2, so on edges, then I have C0, so vertex checks, and face checks again, but I can also put them on faces, and then I have cube checks and edge checks. Okay, but then you can also play with, and you can do this in 3 dimensions, 4 dimensions, and so on. And then you can also play with curvature. And how does this come in? Why is this important? So now, of course, I want to have, there's sort of what's called hyperbolic surface codes. And so they're also tilings of a surface, a closed surface. And topologically, this surface is a multi-handled torus. So of course I could tile this torus with just little squares like I do for the surface code. And then I would encode, 2 times the number of holes in this surface. Right, because every hole I have these 2 loops, and I would not be, maybe getting any benefits out of this, because it is sort of similar as if I would just have, 4 of these donuts separately in terms of overhead, right? But you can actually, so if you use a hyperbolic surface, then it turns out that you can, because of the curvature, and I'll come back to that, you can encode k qubits with n physical qubits. And the way that this is done is that actually, if you were to place the qubits on this multi-handled surfaces, they would not be sort of in a square, they would be sort of stretched out in ways that mimic the hyperbolic geometry. And this fact that there is, if I do this hyperbolic surface tiling and I get this homology, is related to a relation of curvature and topology, a Gauss-Bonnet theorem. Okay, but so there's some math behind it, which I don't think I'm able to summarize here. If you want to know more, you can look at some of the papers. But there is a lower bound on the distance of these codes. And we studied these codes because they are the sort of the smallest departure of the surface code, which gives you a constant rate, so like a tenth or something like that. And but still a growing distance, although it grows fairly. It doesn't grow like, square root of n like the surface code does. It grows like log n. But there is a threshold in these systems, so you can correct many errors above the distance. And you can ask, well, how do I get these things? How do I get these codes? And this is not entirely trivial, but the first thing you can start with is to understand that if you take little pentagons, or you play with papers, and you take pentagons, and you put 5, okay, so let's take squares, and you put 4 squares, at a vertex, of course you tile, flat plane. But if you take pentagons and you put 5 pentagons together at a vertex, then the paper will start to crumble. You can't do this, right? You can't meet the 360 degrees angle this way. And you can see these types of tilings. So there's a classification of what kind of tilings you get. So this would be a 5-5 tilings, which is pentagons, 5 of them coming together at a vertex. But you can also have 5-4 and 3-7. There's a whole variety of these things. And so the way to think about these codes, don't look at this figure yet, think about these codes is that your faces are pentagons. So meaning that the parity check weight is 5. And, every qubit is touched by 5 pentagons, or, no, sorry, that's not what I'm, okay, so no, sorry, the parity check weight, both for the X and Z check, is 5, because every vertex is touched by 5 pentagons. So so that's sort of, give you the parameters of the code as well. And what we did is we studied, we wanted to know a little bit also whether there's some sort of, advantage near term in terms of using these types of codes. So look at a small example of these codes and look at the threshold. And for example, what was interesting is that for these small codes, a few of them turned out to be nicely embeddable, representable as geometric figures in 3D, which is not, well, we can have an embedding in 3D, because if you can look at this multi-handled torus, you could say, well, the qubit connectivity somehow on the surface, so I could sort of have a bilayer in which I have, I slice this sort of multi-handled donut, and the qubits that are on the top, I put on one plane, the qubits in the bottom on another plane, and then I have to still have some connections between these planes. But anyhow, so but for the small case, you can actually have a very nice geometric picture. And so here what we see is called a small stellated dodecahedron. So it's a dodecahedron with and the edges are extended so that they come together. So if you have a dodecahedron with pentagons, you extend the edges so they become these sort of points. And then the qubits, they live on edges. Like, for example, there is one qubit over here, there's 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 one qubit over there. And those 5 qubits, you do a check on those. And at every point here, you see also, this is like a vertex, you see there are actually, well, you can't see, but there are 5 edges that are coming out. And that is the other X checks. Like for the Tor code, you have 4 edges coming out of a vertex. Here you have 5. So we studied this a little bit, and this is a small departure from the codes, the surface code towards codes which have constant rates. Although nobody's done anything with this, and the threshold's also not so great. But if you want to learn more, you can check out this paper. All right. Okay. So here is actually so. Maybe this is slightly, this whole thing about hyperbolic surface code, why is this so important? It's a bit of excursion, but maybe I want to use this as a sort of a motivation or a point to say a few things that would be nice if we can somehow, because coming back to this early question, we really want to just have a fault-tolerant scheme in which information flows, forward in time, being embedded in space. Can we somehow use homology directly to construct these schemes? But now we use the homology to construct the spatial thing. And then say, oh, now we have to measure the parity checks and be fault tolerant and so on. But can we kind of, use this to directly get fault tolerant protocols by also including the time dimension somehow? Now, the point is I don't really know. And there are some ideas also on codes that you can get from, if you have a fault-tolerant scheme, you can associate a code with it, a subsystem code or a history code, and that characterize, and the distance is related to that of the original code, that characterize some of the sort of behavior with respect to errors. But it's not clear that this is, first of all, in these homological codes, I don't have a subsystem code, and it's also not clear that this is the right formalism quite. All right, so that was one comment. And the other comment I want to make, pointing to some research that I'm interested in right now also, is that, of course, these homological codes, I started with Z2, so I started with qubits. I can also start with QDITs, and I can start with R, and I can start with Z. Right, so there's several choices, and I can start with something even maybe more, not more obscure or rich. Okay, but so these generalize sort of CSS codes to other settings in the sense that if you do, for example, R, then you are imagining that your elementary degrees of freedom are not qubits, but are oscillators. And you can have the whole formalism back there. And if you do, for example, Z, then you imagine that your Hilbert space, your qubits, well, it's not a qubit, but it is what I call rotor. It's just an integer, any integer in Z, right? So it's an infinite dimensional space, but maybe you want to use only part of it. And then with many of these, spaces, I want to build a logical rotor or a logical qubit. And the point is that there are things that are different or fascinating for these extensions also that one can explore. Right? So this homological connection with homology is interesting. All right, so I'm actually going sort of... Okay, so now other code constructions. Yeah, so what I want to do in the rest of my presentation, I want to talk a little bit about subsystem and Floquet codes, because that's another sort of, novelty that you may have heard about, that you would sort of wonder about. But before I do that, I want to mention a few other things that maybe you've already touched on. So there are also, I've mentioned the color codes, and they are not, they have a sort of different construction because there's some constraints on, this is not just a tiling of a surface. This is not how they come about, or they can be related to surface codes and homological codes. But they have nice features like the 2D color codes have this transversal Clifford group, and the 3D color codes have a transversal T-gate, as I mentioned in answering a question. But I think I already covered this thing, how you would use such a T-gate. Now, there's another important construction. So I mentioned also in response to somebody, so in 2021, there have been a variety of constructions for good quantum LEPC codes. So they have constant rate and constant d over n. And this development, which I think is sort of still settling down in some sense, because people come up with simplified and new constructions and so on, had its origin in a construction by Zeemer and Tillich in 2009, in which they said, which is referred to the hypergraph product construction. And so actually, so what they do, so let's say the Zeemer and Tillich, what they did is they took two good classical LDPC codes. So there you have a constant rate and a distance that scales with n, and your checks are local. So you get two of these codes. And note that you can see each one of the codes as a chain complex of length 2, right? Because that's what we just did. We said, okay, I have a chain complex of length 3, and one part is one classical code, and the other part is the other classical code. And then they take a construction which can also be viewed as sort of taking a tensor product of these two chain complexes. And they got and then you get a chain complex that is longer, and that allows you to get make a quantum LDPC code with a constant rate, but with distance that scales as the square root of the number of physical qubits. Right? And so you can see that as a tensor product of length 2 chain complexes, and then you can say, well, but then I can also take tensor products of length 3 complexes and things like that. Right? So that and they call this the hypergraph product codes, but yeah, there's different ways of seeing this. But this thing with the square root n, I think for a long time was sort of like, okay, maybe there's some limit. We can only get the square root n distance if we also want a constant rate. Right? We can't get this. Good quantum LDPC codes do not necessarily exist, perhaps. Okay, but so this was proved to be clearly false with various papers in 2021, various authors, which I'm not listing here. So that's a cool new development, although the impact on the practical quantum error correction fault tolerance is still not entirely clear. All right, so I want to talk now about subsystem and Floquet codes. Also to show that there's opportunity for novelty there or has been realized. Is there any question that people want to ask at this point? Yeah.
A question about etymology. What's the history code and why is it called the history code?
Okay, so yeah, that is the history code. So this is sort of, okay, so this relates to a very different area of quantum information processing where they use the history state. At least this is what I think is the case. So, okay, maybe it's this. You have a circuit. In this case, you have an encoding circuit or a quantum error correction circuit. And, that has space and then time. And what you're doing is you're trying to construct a code that has qubits in it that have a space-time label. And so instead of, so basically before and after each gate, you construct a new code which has qubits there, and there's checks acting on qubits there. Why they call this the history code is because it's, okay, so now I mentioned this history state. So there's another construction which it takes a circuit, and then that only has, so it only acts on space, and then it takes time and it makes that into a new register, and then says, the output, I construct something called the history state, which is the superposition of all states at different time slices. But the point is, okay, so essentially it's a way of sort of quantizing time, including time. Like if we ever run a circuit or an encoding circuit, time is classical, and you're going to construct a new object that has qubits that are, sort of related to time slots in the original circuit. Does that help a little bit?
Yeah, a bit. Yeah, thank you.
Yeah.
Hey, back here. Back here in the pink.
Okay. Yeah. Sorry. Yeah.
Thanks for talking about homology. I have kind of been kind of surprised because I started reading more about error correction. I was like, so much algebraic topology. I think I have two related questions. One, the comment you made up here about getting a fault-tolerant QEC scheme based on homology, you just mean rather than just the error correction scheme, additionally have the fault-tolerant layer from homology.
Yeah, the point is now we have a code which acts on qubits, and then I have to measure my parity checks, and then I ask where are the errors in that, and is that fault tolerant, and how errors propagate.
Yeah.
And I'm not getting that from homology, I'm just getting that from, Yeah.
So then I think related to that question is, like, I haven't really been able to understand why we should expect algebraic topology and things like homology to be so useful for error correcting codes. And I guess my guess would be that we kind of have some implicit geometry because qubits are physical and laying on some space, and then the structure of like all the error correction we do is very algebraic. And I guess maybe at the intersection of those two, we just find algebraic topological tools.
Yeah, well, okay, so I'm not an expert in algebraic topology. What I do know is there are these, there are tilings of hyperbolic space, four-dimensional. I mean, there are ways of constructing certain codes that are based on, concretely realizing some manifolds with tilings and so on. And you don't come up with this that easily, in other ways. And then they have, four codes based on four-dimensional hyperbolic space, for example. Like how would you construct these? And they have very favorable properties. And you need to understand some of, Okay, so maybe that's it. But I don't know whether if you say algebraic topology, you also use spectral sequences, but I don't fully understand that. So there are some overlap, but I haven't seen the full. It's also limited, maybe, but maybe somebody else has better ideas here.
But people also use spectral sequences. Do you have like a paper in mind that uses those, or an author name?
Yeah. Okay. So maybe I don't know. Maybe you should come to me afterwards to see if I can. I'm not 100%. I have some papers that I think about.
Thank you.
Okay.
Yeah.
I have a short question on the last line on the slide where you change the field of the homological code. Is this related? Like when you take the field R, is this related to continuous variable systems?
Yeah, in that sense, yeah. But for continuous variable systems, there's several, code families that you can define. I mean, maybe you've seen this. If you have one continuous variable system, you can, bosonic, harmonic oscillator, you can try to encode a qubit, and you can do that with a GKP code. But you can also take, I have, many bosonic modes, and I want to encode a logical oscillator in those. And therefore, I take some linear combination of quadratures. I don't know if people of x's and of the, you know, every oscillator has an x and a p, and I take a linear combination of these x's and p's, and they have to be, I say on the code space, they have to be 0. And there's also called nullifiers, and that actually, you know, is just it can be seen as a homological. Well, okay, some of them can be seen. If I take linear combination of the x separately and the p separately, it can be seen as in this homology sense. But the point is, they encode oscillators, and there are also proofs that these codes don't work very well. But for rotors, we have some ongoing work. I don't know, this may be the people with whom I'm doing this, that actually you can also encode qubits. So it's slightly different, and that's because of some features in the homology. Yes, okay. Yeah, Sergeant at back, yeah.
My question also concerns about the last line. These homological codes over, over Z. I wonder if you can explain a little bit more about these codes over Z and whether they are stabilizer codes.
Yeah, well, okay, yes, I would say they're stabilizer codes, yeah. Because you do say that the code space, well, okay, so you have a commuting set of operators, and you say that the code space is a +1 eigenspace of this. And they are specifically kind of like CSS stabilizer codes, yeah.
And you also mentioned that there are structures beyond and more richer than Z, ZD, or R. What are those structures?
Oh, you mean other codes? So there are, well, there are codes that are in 3 dimensions. There are codes that are like XX. The checks are XX, YY, ZZ. I mean, there are other codes that are not CSS. You can map all codes to CSS code with some minimal loss, but maybe looking at these codes natively is more interesting.
Yeah.
Okay.
Thanks. All right.
Yeah. Yeah. No, there is a very old paper by David DiVincenzo and Asher Perez on code words always violating, being non-contextual or non-contextual. I always get confused about this. But there is, because they're highly entangled, and then you can look at the, some observables. I don't know. Perez and DiVincenzo, if you're interested in it. Sorry, what?
Looking for contextuality, do you have good model for looking?
No, I don't think. I think the goal there is very different. I mean, I do have one thought, but it's kind of vague. So the point is, what I see a little bit with error correction is that what we're trying to do with error correction, we add information about the errors that have taken place, and we kind of want to understand what the dynamics is. But we say, one model is that we say, well, we assume poly errors happen with probability P and then they spread. And you could say, well, can I detect deviation from, and that's sort of a classical error model, okay? Because if the original circuit was Clifford gates plus poly errors, I could classically simulate it entirely. But I think there are sort of deviations from this which may turn up in the errors, like there's coherent errors. But there's maybe also other errors in which you say, like, these can only come about because the dynamics is fundamentally quantum or something like that. So I wonder whether there is a way in which I can treat the stream of error syndrome I can get out in terms of saying how quantum this underlying system, how quantum I have to describe it. But like I said, it's a little vague, so... yeah.
What did they do in the 2021 work to make the square root 2 linear?
Oh, well, this is a whole development because it was first, this is not so this was first a paper with Hastings and others to break this sort of square root n bound, I think with a log vector. And then it was another, not square root of n, but some higher power. And then finally, Karlachev and Pantaleev showed that you could reach this, it was conjectured earlier, but you could reach this a linear distance. And the way this comes about is well, taking a tensor product construction, but also using some symmetry. So I don't think I could be summarizing this, because also now there's several constructions, so it's maybe, yeah.
Okay, thanks.
Yeah.
Hi, Professor. My question is along the same line as others on the homological codes over different algebraic structures. So I wonder, you said that it can have different features. Would you, could you expand a little bit on that? For example,
Yeah, okay. Yeah, okay. Well, feature, because this is very brief. And so the point is, for linear oscillator codes, you can show there's actually no threshold whatsoever. Because these codes encode, logical oscillators, and you say, well, what could I do with encoding a logical oscillator? But you could say, well, is then the sort of, depending on what errors you put on the original oscillator, but you can say, well, maybe the probability for large displacements, as you have them oscillator, is now reduced in some way. If the original, probability of this Gaussian displacement is low enough, and this, gets better with increasing distance, and this is not at all the case. So this is different. For rotors, it is also more subtle whether there is a threshold. And it relates to other, the decoding sometimes is related to StatMech models, and these are then Z2 gauge series for the surface code, and these become U1 gauge series, and they become other gauge series, and they have other phase transition behaviors. So there's other features. But there's another thing that I can just mention is that if you put, so if you have if you tile a Möbius strip and you have qubits, then you can encode a logical qubit. If you do it with rotors, then you actually don't encode anything. And if you do it with oscillators, you don't encode anything. And if you do it with rotors, you also encode a qubit, which is curious because you start with rotors, meaning that every system is an integer, but you actually encode a qubit. And this is because of some torsion in the related to the homology. So there's some connection with homology there. And this torsion is not present if you have Z2.
And in addition to the threshold, would it be helpful with the time-space complexity or time-space overhead of the gates, the logical gates in this code?
Whether these constructions, well, I see more of these types of code. See, the point is, and I come back to the last, qubits typically are not natively qubits, right? We just take a two-level system out of a larger system. And then you can ask, for example, transmon qubit is used in superconducting qubits, are the lowest two energy levels of an n-harmonic oscillator. So the other levels are, slightly not, it's not harmonic, it's not equidistant energy levels, but then you can say, can I use the larger space, or maybe I can just start with a harmonic oscillator? Can I use that space because that's natively available to encode things? And sometimes that's just sort of more hardware efficient or better suited for the hardware. Yeah.
Thank you.
Oh, I was just wondering, for the chain complex, is it like a similar idea to like the Viterbi code and like having like a trellis and all that stuff, or is it different?
So the Viterbi, is that on the, and what did you say, Viterbi?
Like, just the Viterbi algorithm, yeah.
Yeah, but that's on decoding, right? Or
yeah, that's right.
I don't fully, I don't think there's any relation, but yeah. But this is just this is a code construction. It doesn't say how you decode, yeah. At least, yeah, I haven't discussed that, yeah. All right. Okay, so let me now go to the, so first I want to explain what a subsystem code is, and then I want to explain why the subsystem code definition actually misses something that was then later realized. All right. So the subsystem code, you could say, well, okay, why do I need to measure this commuting check? So the subsystem code is sort of, you could look at as follows. You say, I have my poly group, so P. And now I start actually not with an abelian group, which I can identify as a stabilizer, but with something that could be a larger group, G, which elements do not necessarily commute. And that's this sort of light beige thing. And the idea is, why would I do that? Well, the idea is that these G elements in the generator of G may have very low weight. And typically I'd like them to have weight 2 and maybe on the lattice. And then I say, oh, I only need to, and I want to only measure those. Because why do I want, then, you know, a weight 2 check is easily measured. I only need 2 C0s, so less error prone. Sounds good. Yeah? Okay. But of course, if elements in this are not commuting, then, you know, let's say it's an XX here and a ZZ there. If I measure this XX, get eigenvalue, and then I measure the ZZ, and then, you know, the ZZ will have random eigenvalue if I'm in the eigenstate of XX. And if I measure the XX, so these eigenvalues will be sort of random. So I can't use them to detect errors because they're just flipping all the time. So so another way of looking at this, I'm actually I'm interested also in this group, which is abelian, because I'm taking all elements in G that commute with each other. So I'm constructing elements in G out of these sort of weight 2 things that are commuting with everything. And so that I call the stabilizer. So that's in red. So then I could say, well, once I have that, I could just treat it as a normal stabilizer code, meaning this S, there will be some C of S, that's this yellow thing, and those are the logical operators of my stabilizer code. Yeah. But then I can say, well, what about this G now? Because I'm measuring those. So if I'm using all the logical qubits that this stabilizer code encodes, I'll be measuring properties of logical qubits. So actually, there should be some of a separation where there are operators out here which are not in this G, and those are my real logical qubits that I want to protect the information in those. And then out of what's in here and not in there, I can construct what we call gauge logical qubits. So these qubits, if I measure these Gs, they have their state fixed or changed. And, you know, sometimes they're in the +0 state, and then they're produced in the plus state, and so on. And so by actually, you know, I'm going to measure these operators. So I change their state, but I don't care. I don't care about messing up their state, right? I just care about the logical operators here. Yeah, so they're the protected or chosen qubits. And so the point is that because S is contained in this, by measuring these Gs, I have to be a bit careful how I measure, I can construct the eigenvalues of S. And I use S for error correction. So in some sense, this is just like a stabilizer code, but I could have started with S, and then I just my CS, but then there may not be a G with weight 2 operators. I may not find it. Right? And I would like to measure the stabilizer of S, maybe they have weight 6 or something higher, by measuring these weight 2 checks and then combining them to get these elements. And so, you know, the distance of the code is anything, the minimum weight of stuff that's out here. It shouldn't be in G, it should be in there. Okay? So now an example of this code is the Bacon-Shor code. So now don't read this necessarily. But so the Bacon-Shor code is, here I see a small example, 9 qubits. And this group G with these non-commuting things is generated by vertical XX, so XX here or XX there. Yeah, on any one of these things, only all the vertical edges. And the horizontal ZZ here. Clearly, they don't commute, right? And now you can ask, of course, also what's in S, right? So I have to construct sort of products. For example, I can construct, if I have this vertical edge here, so these red, so I have X, 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 then that's clear that it always commutes with these ZZs, right? So this sort of double row, if I make this code larger, double row and double column operators of X and Z type that generate the stabilizer. And for the Bacon-Shor code, these stabilizer things are very non-local because if I make this larger, they're all the whole thing. And this is why actually, if I make this Bacon-Shor code larger, then because these are very sort of high weight, then the number of stabilizers is actually, you know, not scaling with the system size, and that means for larger code distance, for larger codes, I get too little information. I got to take care of n squared qubits, n by n lattice, but you know the number of information bits I'm getting scales less than n squared, so I can't keep up at some point. So this is why the Bacon-Shor code roughly doesn't have a asymptotic threshold, but it is a code that's used, you know, can be used for small things. And what you want is you want to measure these checks and then say, oh, I can combine their eigenvalues into this sort of double row operator, and the same for the z-checks, and that's what I use for my error correction. And then you can also what we call gauge fix. So you can say, well, if I, you know, all the gauge qubits, so there's some, you know, gauge qubits here that I have, you can put them in the logical Z state, and you can actually get a stabilizer code. So you can gauge fix them this way, and you get this stabilizer code, you can gauge fix them other way, you get another code. Okay, but I don't want to actually mention that. All right, so now let's move to the point of what I learned about this Floquet code, which you may or may not have heard about, is that the subsystem code formalism is just too restrictive. It's just, it's not fully general. Because you're saying, you're starting with this gauge group, and then you have the center, but you're not specifying this measurement of these gauge checks. You're saying, well, you know, we somehow measure them so that we learn S. But you're not leaving the room, you're sort of not, yeah, you have to specify, and this comes into also in this direction where we should be talking maybe about schemes for measuring whatever, you know, non-commuting stuff, and how this propagates information forward in time in a fault-tolerant manner. So we in this paper, actually quite an old paper, we thought, okay, well, we know a model where it looks like a subsystem code, and this is the honeycomb model on a torus. So here in this honeycomb model, I have X checks going this way, Y is maybe too small, while you see here, this is an XX, this is a YY, and this is a ZZ. So the anti-commute on that single overlapping qubit. And so we thought, well, let's first establish whether this has a logical information. And then to our, you know, unfortunate thing, we could prove that there was nothing encoded because, well, okay, so what you do is you say, okay, what's in S? And in S are sort of closed loops. So you take these links and you kind of take products of them and you construct loops. And these loops could, of course, also go around the handle, and they can go around the little plaquette and so on. And then, and that's, so everything that you make for these links, there are these loops that is in S, and there's nothing in the CFS is left. So we thought, okay, it doesn't work. We have to, so we constructed more complicated codes. So, and they didn't have such a great threshold. But the point is that the stabilizer that you are currently in, meaning that their current state is the +1 eigenstate of that stabilizer, is not necessarily equal to that. It can be less than that, and therefore there's some, you know, there's some logical that is, you know, there's some freedom that you have that you haven't used. Okay, so then came around what is it, Hastings and Ha, and then some follow-up work, and I think it's still ongoing, with what they call the Floquet code, or dynamical qubits, or so dynamical logical qubits. And so they said, okay, we need to have first, we do a rounds of measurements, and we have two stabilizer groups associated with it. And one is what's called a perpetual stabilizer, which is sort of, if there's no errors, this always should have +1 eigenvalues, and this is what we use for error correction. And we need to, of course, learn the eigenvalues of this perpetual stabilizer by measuring the checks. But okay, so this is not so important. And then there is the instantaneous stabilizer, and that was the point, the instantaneous stabilizer. Okay, so what we do is we measure, say, the red links. So these are these guys. And now, after that, you measure the blue Z links. So these guys. And then you see that the blue links and the red links, if you take, they go around one of these guys, these plaquettes. And if you take their product, you get a Y around this plaquette. And so you can record now the green Y stabilizer. That's an element in this this stabilizer that you use for error correction. Now you measure the green Y links. So then that, you know, so over here. And then you look at, oh, okay, I already had the blue Z links, so green and blue. Now I can take this one, the red stabilizer, right? Because they circle around the red stabilizer. So now I can record the red X stabilizer. And I can do, now I do the red links and I have the blue stabilizer. So I cycle through these, and every time I can update one of these stabilizers. And those sort of phases, they generate this perpetual stabilizer. But then you can talk about the instantaneous stabilizer group. So that includes the stabilizer plus the last measured links, right? Because you just measured, so you're now in the +1 eigenstate of those links, right? And so that is an addition on this in the stable thing. And you can say, okay, what does that code encode? Right? Is in that stabilizer, is there anything that commutes with it but is not generated by it? And yes, it turns out there is. So there are, the instantaneous stabilizer has a non-trivial elements in the poly group that commute with it but are not generated with it. Yeah. So the point is that this thing was not the right way to look at it. Essentially, you could say it this way. Yeah, and so this is now, and then the boundaries. So people have studied that now, and I haven't kept track of all the literature, but I think this is definitely an interesting development because the point is this is sort of the minimal subsystem code that you can come up with maybe the minimal overhead, because you have to take many of these weight 2 checks to construct the stabilizer, the stabilizer used for error correction. That, of course, is a disadvantage, right? You're measuring weight 2 checks, you say, oh, I'm done, But no, I take the product of their eigenvalues, and if every eigenvalue has some probability of error, and I take the product of many, of course, I enhance my error rate. And that has been the sort of the bottleneck also with using subsystem codes in terms of their performance. But maybe this has different features. Okay, so now, wait a moment, it's now 1, okay, so... Oh, we should stop at 1, said Frank. Okay, I'm doing very well on time, so maybe too early even. Okay, so I can say many things about practical error correction, and I want to say one thing, and I've already mentioned it, but just about this leakage thing. Right, so I work with two people that work on transmon qubits, and here you see the energy diagram of a transmon qubit. So this is ground, excited. These are used to encode your qubit. And then there's the level F or 2 above it, which is slightly lower, like slightly going down. And these qubits are realized as electric circuits that are not like LC oscillators, which would be a harmonic oscillator, but there's an element that makes the L of the LC anharmonic and creates sort of this spectrum. So it's an anharmonic oscillator, and they leak quite badly. And there's more, I think there's been more studies of that. They leak to 2, but they can leak to 3, and they may leak to 6 or something like that. And even you don't know where they leak to, because well, how would you know where they leak to? They measure the state of these qubits, and they kind of get, like, for 0, they get a blob here, for 1, they get a blob there, and then you get a blob somewhere else, and you say, well, you call it 101 or whatever, It's like, you don't know, or maybe it's some other, there's something else going on. And of course, the point is you only know that you excite these states because you measure, but your measurement is imperfect, so where does the error lie? Okay, but the point is of leakage that it has a subtle signature because, like I think somebody asked, if I'm in a leaked state and I apply a parity check on that, that includes that leaked qubit, how does that leaked qubit affect the outcome of the parity check? Now, one model is where you say, Well, if, for example, that leak qubit is here, it undergoes a control Z gate with my ancilla qubit that does the parity check. And this leak qubit does not impart any phase on this ancilla qubit. So it's as if this leak qubit is just not there. Okay? So it's as if this leak qubit is sort of well, it's an erased qubit, but I don't know whether, it has there. But the point is that if I were to measure, say I were measuring a weight 4 parity check, and now one qubit is just out, so I measure a weight 3 parity check. And then you see, if you look at the surface code, and, then you see that these parity checks, these weight 3 parity checks, are not necessarily commuting. Sorry, I have to have some water. And if the checks that you're measuring are not necessarily commuting, you'll get random outcomes. So by alternating things, you get random outcomes. So you say, well, if I see a high defect rate, if like the parity checks seem to be flipping, that could be a signature of leakage. But this is not an easy thing to figure out from the parity checks where a leakage has occurred, because you are doing that in the presence of many other errors that you like to figure out. I have to be careful with my throat here. Okay. So it has a subtle signature, I don't think fully understood, because it also depends on the hardware, how leakage, if it enters gates, what it does. But some people have claimed, and I think justifiably so, that leakage can also have advantages for error correction. But this depends very much on you being able to detect leakage. So there is an old way in which people try to encode a qubit, which is called the dual rail proposal. So in this scheme, maybe you can see it. Here, this is from the Yale group. Here they say we have 2 cavities. These are microwave cavities. And there is a mode in the cavity, and you can put 0 photon or 1 photon in this mode, and the same with this cavity, 0 or 1 photon. And then you could say, okay, well, that's 0 and 1, I can use it as my qubit. But that is not such a good idea. But you could also say, well, I could use the 2 cavities to encode 1 qubit, meaning that a 0 is when there is 1 photon here, no photon there, and the state 1, the logical qubit 1, is 1 photon here, 0 photons there. So that's the dual rail encoding, and this is the encoding that's used for a long time in photonic schemes for getting fault tolerance. Where you have 2 optical modes, and whether you have a photon here or there and no photon in the other mode is the encoding. Now, because in these cavities or also optical modes, the dominant source of errors is losing a photon. It's clear that if you lose a photon, you'll go to the 0-0 state. If you gain a photon, which is less likely, you go to any one of these 2-0 or 1-1. But what changes is the photon parity of the 2 cavities, right? So if there is a good way of measuring sort of the joint parity, so in the code space it must be odd, and if you leak to 0, first to 0-0, it must be even. Then you could be detecting this, and if let's say this is the dominant source of noise. And then assuming you can just re-prepare a state in this subspace of 1001, you could be passing that information about leakage detection onto your decoder. And this is a plot. This is from a different paper, which proposes a similar idea but using transmon qubits, similar as this one, but slightly different, also using dual rail encoding. But what this plot is here we see regions, and these regions are below thresholds. And so here is a error probability P. And if on this axis I go all the way over here, then P is just this basically circuit noise as we do for the surface code. So we have a surface code, and after every operation, C0, the measurement, we have some depolarizing noise with probability P. And then we get a threshold of, 0.8% or a little less than 0.8%. That's this point. And now what they do is they say, in addition, after every gate, you can also have an erasure errors on top of this P. And that erasure errors, every time the erasure happens, you get a flag, qubits erased, it's sort of set back, in the completely mixed state in the computational basis. And you can use that in decoding. And so you see that the point is that if you didn't get that flag, or you threw away the flag, then this dark region is the threshold region. So you can, here again, this is the 0.8% here, this point. But here, what you've shown is that if you can tolerate a lot more erasures than regular errors, because you could be sitting over here where your erasure error is like 2%, and maybe then your regular error has to be somewhat lower, but this is all below threshold, right? So this shows that and this is now kind of clear from what I told you before, that you can correct d-1 erasures was a distance decode, so you can do a lot better if you know where the errors have happened. Like this example I gave of the 4-qubit code, that if it would get information where the error had happened, it worked, right? So that's an opportunity potentially here, but it depends very much on whether you can do this leakage detection. And like, for example, the people that I collaborate with, it's not at all obvious how we would detect that the transmon has gone up the higher ladder. It's usually what we actually focus is on leakage reduction. We just say, okay, let's put it back somewhere in the computational space, such that when we hit it with QEC cycles, it just responds normally, right? So that's the, all right, so now, these are just a few comments. So there are many aspects that I've studied that I think are interesting. Decoding needs to do fast. You can do neural networks. We can try to do in hardware using experimental data. There's a lot of work on small code constructions, which are fault tolerant, using clever protocols, which sometimes use additional flag ancillas to make sure that syndrome information points to errors more specifically, right? Because we said if you have to decide whether it's this error or that error, and the product gives a logical, it's bad. But if I make sure that this error has a different syndrome, because I kind of measure something else, then I can avoid that problem. So that's like the use of, so then sometimes protocols that don't look fault tolerant with additional ancilla qubits can be made fault tolerant without too much overhead. So this is Ben Reichert's been doing a lot of work in that, nice work in that direction. That's also seen, experimental implementation. Then there's a whole other thing about biased noise, which is also interesting, where if Z errors are dominant, but this also depends whether you can profit from this, depends a little bit on details of how you do C0 gates and so on. And I've also not talked much about bosonic quantum error correction, which is in particular for these superconducting systems and microwave cavities is of high interest, but also in trapped ions, there's some work on bosonic error correction. Okay, I think I just want to wrap up and leave the floor for some questions. Stop.
Oh, hey, I'm just curious. Is there a way to combine, let's say, surface codes and bosonic error correction?
Yeah. So what you do is, we've written a paper about this also, because these bosonic, so for example, a scheme that people looked at is you have a single oscillator, maybe it could be a cavity with a single bosonic mode, and you encode a qubit in this via the GKP scale, Gottesman-Preskal-Kitaev. And so you have now one qubit in that cavity, but maybe that has pretty good performance, but that's not the end of the road. And so you want to, on top, you want to sort of concatenate that code with, so you want to treat that as one qubit now in a bigger surface code. That's sort of the game. Yeah, and the point is that, of course, if this elementary qubit has easy C0 gates, then that will help a lot, right? And this, for example, GKP, it's not, people haven't done the C0 gate there. So it's a lot easier to do a C0 gate or a control Z gate between two transmon qubits than it is, well, that between two GKP qubits. At least it hasn't been done. So, yeah. And the dual rail encoding also has advantages in terms of 2-qubit gates that they believe are good, and also that the leakage detection will allow you to get better performance for your surface code if you use that. Yeah. Yeah.
Thank you so much. That was very insightful.
Yeah.
Thank you for your talk. And my question is, you mentioned earlier really briefly that you can map all codes to CSS codes with a bit of loss. Could I ask if you could describe how this mapping could be done? Is it an explicit construction?
Yeah, it's an explicit construction. It goes through Majorana fermion codes. Yeah, I can give you the reference. I think it's in a paper, Majorana fermion codes, by myself and Bravi and Leemhuis, I think. Yeah, if you want, yeah.
Thank you for the talk. I wonder, back when you talk about this Flockit code and you use this
The what
Kitai's
code? Sorry.
Flockit code?
Yeah.
A Flockit. And then you said by measuring specific Pauli operators, you realize stabilize the generator. This seems to me like the gauge fixing when we talk about code switching. Are they the
Yeah,
same
they're
idea?
related, or yeah. I mean, you could say I fix the gauge differently every time. And so I go into this instantaneous stabilizer is like the perpetual stabilizer plus some gauge fixing that I change, which checks I measure. Yeah. And that sort of pushes the information forward, which I think.
What do you mean by push things?
Well, I don't know. This is just my way of imagining this. That there's measurement pushes, but I don't know if there's any depth to this. Yeah.
And also, you just said that by changing vertex instead of using faces instead of vertices or edges instead of vertices, you can construct a dual code.
Oh yeah, that's just
That was like in the earlier part.
Yeah.
And what is the benefit of doing this or like using?
No,
this
that's just a way to describe. See, the point is, if you talk about homology, there is homology and co-homology. And I just wanted to say that homology then relates to the logical z's and co-homology relates to the logical x's. Because there's always, if there's a logical z, there's always a paired logical x. So you can say, well, how do I get this? But you can also, well, another way of getting it is you just go from the lattice, the tiling that you have to the dual tiling, and then you go from homology to co-homology. But it's not, it's just a way of having, certain language associated with constructions.
Okay,
Yeah,
thank you.
Yeah. There's a question.
Yeah, thank you for the tutorial. So many of these constructions are based on the complex chain that defines the code. And another practical consideration would be planar or short-range connectivity. So I was wondering if there is a methodic way of studying that from the complex chain that defines the code.
Yeah, because, well, the chain complex you obtain from a manifold. So, of course, if the manifold is three-dimensional, you need three-dimensional connectivity in principle. So that comes directly from that.
Okay, thank you.
But then there's also geometry, right? So their point is that you need this hyperbolic geometry, for example, which means in practice that the qubit, like we have sort of Poincare tiles where the qubits at the boundary are a lot denser than the qubits in the middle. So you can't have the qubits are not equidistant, and so they have to couple more in both short range and long range. But for some things, like for example, for transmon qubits, the couplers are actually resonators, and these resonators can be sort of like, it's like stretched out, or they can be sort of wrapped up. It doesn't change the resonance frequency. So there is actually quite a variety of physical ranges. So a qubit could be far apart. Two qubits could be far apart and couple. If you can stretch out the resonator, the point is, of course, then they don't. It crosses other, if it's 2D, there's problems with other things.
Right.
Yeah? Okay. You hear a question? There's also... Yeah, maybe wait. Yeah, sorry.
Yeah, so I was wondering with the cohomology construction of the codes, is there any natural or intuitive way to see fault tolerance or gates in this language?
Well, fault tolerance. So there's several aspects of fault tolerance where, the fact is, if you have, in these constructions, typically the checks are very local, and this comes from sort of a local tiling of a local representation of a manifold. So, and if the checks are very local, then in principle, just measuring the checks is fault tolerant. But there's also things that, the point is that this is a problem in the surface code. If you measure the checks and there can be an error in that measurement, then you shouldn't react on it. It's not fault tolerant to say, okay, I measured the checks, that's the eigenvalue of the stabilizer, I'm going to correct. You have to repeatedly measure. And there, actually, if you have these 4D codes, or you can actually only have single-shot error correction. So the dimensionality of the manifold determines indeed some property of the fault tolerance, namely that you can measure the checks once, and then you determine the correction based on that. Because actually it's something like that the non-trivial syndrome, they should actually form closed loops locally. And then if there's errors in the measurement, the loops are slightly broken up. So you say, oh, first going to fix my loops up so that they're closed, and then I'm going to interpret what errors they give. So your answer, so there is an aspect of fault tolerance that is influenced by the dimensionality of the manifold. And also in terms of gates, but that is maybe less clear. There are some no-go theorems about, like, you can't do all the gates transversally and so on. So you can't get around that. I know for the color codes, there's maybe 11-dimensional, some high-dimensional scheme, which has the self-correction, but you need to go very, very high dimension. So there is a use, of course, that's the color codes, it's not the homological codes. But I think you can map them onto homological codes. So yes, the dimension plays a role, but not, but then there's also questions about, rates. Yeah, I guess, yeah. Sorry. I think the answer is yes.
Okay, thanks.
There's another question there.
Thanks for the tutorial. So I was wondering, so it seems to me like a lot of these topological codes are motivated by a situation in which you have qubits arranged geometrically with like nearest neighbor interactions, right? Have people thought about a situation in which you still have geometrically local interactions, but that maybe can go beyond nearest neighbor, and how to construct codes for that kind of scenario?
Yeah, I think so. Well, okay, so the point is, I think I've seen a paper in the last year, but I don't remember the author list. So it is something that, okay, I don't have a good answer necessarily. I mean, actually, recently this week there was a paper on, because there's an idea of modularity. So you make a patch, and then that is connected to another patch via some boundary that is more noisy because there's a different chip, or and maybe there's also different connections. You maybe connect this patch to a patch far away. It doesn't need to be geometrically local, say. But this paper studied the noise rate at the patch, and what you could tolerate, that you would tolerate higher noise rates. Okay, so I have no good answer right now. Maybe there's somebody in the audience who has a better, I think it has been studied, but I don't know, there's not like a one thing that I say, oh, this is the right way to go.
Okay, thank you. I did have a second question.
Yeah.
So you mentioned single shot fault tolerance is possible for 4D codes, right? If I forget about geometric considerations for a moment, and I just have a code and I assume all-to-all connectivity, are there standard like gadgets, something like a flag qubit scheme that you can use to construct single shot fault tolerance for a given code? I don't know if the question made sense.
Oh, you mean that okay, so you're saying now I want to, so okay, single shot exists for 4-dimensional codes, but now I want to do it for 2-dimensional connectivity within Scylla qubits, or?
Something like that. But I'm willing to give up like sort of geometric locality for interactions for this.
Yeah, well, I mean, see, the point is you can actually, this whole concatenated scheme, you can do in a 2D manner. We've worked this all out. So in that sense, but that's not maybe a single shot. Well, it's kind of incomparable, but yeah, okay, so the point is, because you want to stay with topological codes, but then I think the single shot nature is tied to the dimensionality. It's hard to get around it. Unless you're really going to get a very different ancillas, and then maybe it starts to look more like this concatenated scheme. Yeah, so then the question maybe is not completely clear what you allow yourself in terms of, yeah.
Okay, thank you.
Yeah. Okay, maybe we should wrap up, or some more questions? Okay, I think we should go for lunch. Okay, thanks for your attention.